Okay, so today we're going to learn a different approach to clustering that is more probabilistic in its construction, and it's going to use a model called Gaussian mixture models. So just to start, let's remember a little bit about multivariate Gaussian distributions. So we've seen these, for example, when we talked about linear regression. We talked about how linear regression connects to maximum likelihood. We said if you assume noisy Gaussian measurements, basically, or noisy Gaussian targets, then that's where you get this connection with the multivariate Gaussian. So multivariate Gaussian is just like a multidimensional Gaussian, and I think we've all seen this probability density function before. So basically there's a scale factor that doesn't involve x, the variable, nor the mean. And then you have an exponentiated negative quadratic form that involves x and the mean. And q is the covariance matrix. And so we usually abbreviate this density like this. X is the main variable, mu the mean, q the covariance. And one of the interesting things about this is if you look at samples that are drawn from this density, or if you actually look at the density itself, this would be examples where we have like x1 and x2, so two-dimensional case. And you want to know like how, what is the shape of this? Or what is the shape of one of these equal probability cuts? Those are ellipses. And as you might remember, an ellipse is characterized by its principal axes. So there's that vector and that vector. It turns out that when you take this covariance matrix and you do an eigenvalue decomposition of it, the V, the eigenvectors, are exactly the directions of the principal axes. And the eigenvalues in the diagonal here tell you exactly how they are stretched to form the ellipse. So they're stretched by square root lambda. So basically this eigendecomposition that we studied in the context of PCA is actually super useful just to understand multivariate Gaussians. It really tells you everything about how that Gaussian is stretched within the larger space. Okay, so that's where we're starting. Any questions on the multivariate Gaussian? Okay, so the model we're actually going to be using is a mixture of those multivariate Gaussians called the Gaussian mixture model. And it has this form. So here we have a total of k, capital K, different multivariate Gaussians. They can each have a different mean and covariance matrix, and they can be weighted by some numbers that are somewhere between 0 and 1. And these numbers must also add up to 1 in order for this sum to be a valid probability density. So we need this to integrate to 1, and that happens as long as the gammas satisfy this equation. So basically, I want to emphasize that what we're doing here is we are doing a linear combination of densities. It's not like we're doing a linear combination of random vectors. In fact, if you have two different random vectors, x1 and x2, that come from different Gaussians, and you add those random vectors up, it turns out that the sum is distributed still from some Gaussian. So we're not talking, this is not a Gaussian, this is a Gaussian mixture. So really, we're not talking about adding or averaging random vectors x, we're talking about averaging PDFs. And when you do that, you get pictures like this. If you look at the dots, this would be like the scatter plot. If you look at the cost contours, that would be referring to the density here. But as you can see, Very different from a Gaussian where there's a single hump. In a Gaussian mixture with capital K components, there's going to be K humps. That's the difference. And so when you look at this overall picture, it looks very similar to what we saw with clustering when we first introduced or motivated the problem of clustering. It looks like this could be a really natural way to do clustering. If you're given a point, somewhere here, and you want to say, like, is this coming from a cluster of data? Or let me go back. If you're given a bunch of these points in your data set, all of these guys, and you want to know, like, a way to cluster that, maybe we could just fit a Gaussian mixture model to that, which would put one Gaussian over here and another Gaussian over here. And then if you got a new point, to figure out which cluster this corresponds to, you could just compute what is the probability that this comes from this versus the probability that comes from this. That would tell me whether this is more or less likely to be in this cluster or that cluster. So there's a really direct match between Gaussian mixture models and the clustering problem that we're trying to solve. Is that sort of clear? At least just from looking at this picture, how it suggests a way to do clustering. Okay, any questions on anything so far? Okay, so that's basically what we're going to do. So at a high level, given our data set, which is all these dots, we would first somehow find the Gaussian mixture model parameters, which would be all of these gamma k's, mu k's, and q k's. And then once we have them, for any point in our data set or any new test point, we could essentially evaluate the probability. We just plug that point into our density, and that gives us a number. We're going to plug that point into this, and then that gives us a number, a probability that is larger if it's closer to one of these densities or one of the clusters. Okay, so to understand this a little bit better, we would like to kind of decouple this into two parts, two stages. And maybe a motivation for that is, let's say that you were interested in using a Gaussian mixture. Someone gave you a Gaussian mixture, meaning they told you all these parameters, and then you wanted to draw samples from it. Maybe you wanted to make a scatter plot like this. So how do you do that? So basically the way that you do that is a two-stage approach. You first choose which cluster of the two or of the capital K that you're going to draw the sample from. And then once you know the cluster, then you just draw a sample from a Gaussian, which is pretty straightforward. So this is basically the two stages. First, draw a component index, which we're going to call kappa. Kappa is going to be an integer from 1 to capital K, which basically just tells us which cluster or which component it comes from. And then once we have our kappa, we just draw X as a Gaussian with mean mu kappa and covariance q kappa. So that's a pretty standard procedure. Okay, so why can we do this? Why can we break this density into these two stages? So let's just do a short proof. So for any PDF px, we can always add this extra variable, in this case kappa. So now we have a joint PDF over x in this new variable, as long as we integrate or sum over all the possibilities from the new variable. That's just called the law of total probability. Usually we do it in this direction, but here we're kind of doing it in this direction. And now if you have this joint probability px and kappa, we can use conditional probability to say that's px given kappa times probability of kappa. And now this px given kappa is basically just, what's the density of x if I'm in the kappa component, or if I'm coming from that component? That's just this Gaussian. And what is the probability that kappa equals the value k? That's just the weight gamma k. And this is a valid PDF or PMF because of how we scaled it. Okay, so basically, this is exactly the Gaussian mixture model we started with. So hopefully, this convinces you that yes, we can actually break this problem into these two different pieces. First, think about drawing this discrete component index, and then draw x given the component index. And this is an example of something that happens in many other ways in statistics. It's an example of what's called a hidden variable. So it's a hidden variable because there's really no kappa in the original statement of this Gaussian mixture model. Kappa is something that we kind of constructed to make our life convenient. And there's many, many other ways to choose hidden variables in different statistics problems, and they're just always done to make your life easier somehow. So this is how we're doing it in this case. Okay, so that's basically, at the end of the day, this is like another way. Oops, maybe this is the one. This is another way we can think of our Gaussian mixture model. The probability, the PMF for kappa times the probability for x given kappa. Okay. Any questions on this? Okay, so kappa is really the key for clustering. So let's say we somehow already know the Gaussian mixture model, meaning someone has told us all these parameters, and now we're given an x, and we want to say, how should I cluster that x? Which cluster does it correspond to? It's basically saying which is the most probable kappa given x. This posterior probability. Probability that kappa equals some integer k given x. That's really, so this is going to be what we call a soft assignment, meaning, this is a number somewhere between 0 and 1. And so maybe just, for example, if I have a point over here, then the probability of this point, probability that this point comes from here might be almost 1. The probability this point comes from this guy is almost 0. But if I have a point over here, probability that this comes from this might be 0.5 and this might be 0.5. So that just says that some of these points are more difficult to assign to a component or cluster than others. But still, at the end of the day, if it's greater than 0.5, we can just round it up to 1, and that's going to give us some kind of decision boundary. It won't be straight. And all the points on this side will basically have these kappa probabilities that are larger for this component than for this component, and so we would cluster them all along with that component. Okay, so that's essentially why we're interested in this. And then this is how we do the hard assignment. We just look at this for all the hypothesized different k's, and whichever k is largest, that's the kappa that we have finally assigned to that x. So this is how we're using the Gaussian mixture model for clustering. It's all about these hidden variables kappa that basically tell us which component x came from. Okay. Any questions on that? Is this kind of making sense? Okay, so one more thing we have to do is we have to get this is sort of like this super important term, we have to get this into a form that we can compute, because it's not obvious what is the probability of kappa given x. So we can use Bayes' rule to swap the ordering here. So that gives us probability of x given kappa times probability of kappa divided by probability of x. And it turns out that we know these things. So probability of kappa given k is just gamma k. probability x given kappa is just this Gaussian where we have k over here. And then this probability of x is basically, probability of x is this expression. So we can plug that in over here. And now we have an expression if we know the Gaussian mixture model, so we know all these parameters, and we know x, then we can compute this probability. Okay, so this is something we'll use later. Okay, so that's how we're going to do clustering. And just sort of a summary of what we've said so far. So usually we start with the data set. We don't actually know the Gaussian mixture model parameters. So we start with this data set. And so our first step, which is going to take a bit of explanation, is how to fit all these Gaussian mixture model parameters to our data set. We'll talk about that later, but assuming we can do that, now we know our parameters. And now we said for every sample in our data set and every hypothesized cluster index k, we compute those probabilities on the previous page. And finally, we just look for the k's that maximize this. That gives us our hard assignments for every value I in our data set. So that's the overall procedure of clustering. The hard part, the thing to talk about next, is how to figure out these parameters. Okay, any questions on the overall approach of how we're using the GMM to cluster? Okay, so how are we going to fit these parameters? So as always, we would like to use maximum likelihood, but this is a bit challenging in this case because the likelihood is not convex in the parameters. It can have some bad local minimum and so on. It's difficult to maximize. It doesn't even simplify well. So usually when you have a single Gaussian, if we had a single Gaussian, we would basically, our likelihood would look like this. And there you have a log of a Gaussian, which is quadratic. It's very nice to work with, right? And that's exactly what we used for linear regression. Basically, the log cancels the exponent in the Gaussian. That's where you get that quadratic. But here, the problem is there's a sum in between the log and the Gaussian. There's no way to simplify this. So we don't get the cancellation of the log and the exponential, and you're stuck. Okay, so in order to work with this, we're going to learn about a new approach called the expectation maximization algorithm. And all right, so the EM algorithm is an iterative algorithm, and it's an approximation to ML estimation that is very handy in cases where you can't directly solve ML. And the guarantee you have for EM is it's guaranteed to converge to a local maximum of the likelihood. But of course, that's not really what we want. We want that it would converge to the global maximum, but that's too hard to guarantee in most cases for these difficult problems. So using EM is often a matter of coming up with a good initialization that puts you in the region of attraction of the global maximum and then running EM. So often you need a good initialization, but that's just how EM works. Okay, but EM is still a super useful procedure, and so that's why we're going to learn about it. Now, the algorithm basically is these two steps. You just iterate back and forth between the first step, called the E step, the expectation step, and the second one, called the maximization step. And the key here is to introduce some hidden variables for whatever problem you're working on. And those hidden variables are variables such that if you knew them, things would be really easy to estimate your parameters, theta. But without them, you're stuck in this difficult situation like we are here. So the idea is if we can come up with a good choice of hidden variables, maybe we can use that to our advantage. But the thing is, these hidden variables, unlike our data X, our hidden variables are unknown. And so because we don't know them, it's sort of a chicken and egg problem. If we knew them, we could solve our problem easily, but we don't know them. If we knew the theta vector, the thing we're trying to maximize over, we might also be able to infer our hidden variables, but we don't know theta either. So essentially what you do is you start with some guess, and you compute this quantity, which I'll talk about in a moment, and that quantity will depend on whatever current guess you have for theta. And this quantity is also a function of theta in terms of something you can maximize to improve your guess of theta. So basically you alternate between somehow computing this function given your old theta and then maximizing or optimizing that function to come up with your new theta. And you keep iterating back and forth. Okay, so I'll give you some pictures and some intuition in a moment, but first let's actually take a peek to even understand what this thing is, because it's a little bit complicated. So let's look closely. It's an expectation, and we're taking the expectation of this quantity, but this thing in the subscript tells us how we're formulating that expectation. So notice this is an expectation over z. Z is the random variable that we're taking the expectation over. We're treating x, which is our data. We're conditioning on it. It's fixed and known. It's just the features we know. And then we're also treating theta, which is our previous guess of our parameters, as fixed and known. Okay, and the resulting thing we're going to get is going to be a function of the data and a function of theta, and that thing that's a function of theta is what we will maximize over. So let's take a closer look at this. So this is elaborated down here. So if you remember the formula for conditional expectation, here we have the thing we're taking the expectation over. We need this probability density inside the integral. Here that is. And then we're integrating over z, which means our integral is over z. Okay, and so now when you think a little bit more about this, this is just a weighted average of this thing, where the weights are the probabilities for all the different possibilities of z. So in an extreme case, and z is basically, z are the hidden variables, and this probability of z is basically like our best guess of z in some sense. Of course, we don't really know, we don't think that z is any one value. That's why we have an entire distribution describing what we believe about z. So in one extreme case, maybe we are absolutely sure that z equals the fixed value z hat at time t. In that case, our belief is this spike, this Dirac delta, where all the probability mass is concentrated at this value. And if you plugged this into this integral, then things would simplify, and you would find that this Q function is just like the joint probability, the log of the joint of the parameters and our guess. And basically at this point, it looks a lot like the likelihood that we want to maximize, but with this this guess of our hidden variables that we're very confident about. Now, in reality, we don't have this extreme situation that we are absolutely confident that z is the z hat. We actually think, well, z could be this, it could be that. We don't really know, and that's why we have this whole integral over all what we believe about the possibilities of z, given our data and given the parameter guess that we have at the moment. So that's just trying to give you a bit of insight into what is this Q function. Okay, so a lot of details here. Any questions before we move on? I'll try to explain it from a few other perspectives now. So, so this is, I think, probably the best expectation of why EM is formulated this way. And it starts with the basic log likelihood. This is the thing, remember, that we would ideally like to maximize. So for a log likelihood, and for any hidden variable z, with any belief about that z, some PDF p hat z, we can always write this in this more complicated form like this. Now this is because this is an integral over z. This log probability doesn't involve z, so I could pull that out front, after which the only things left in the integral would be this, and that always integrates to 1 for any probability density p hat, right? So basically this is just like a complicated way of writing this. Now let's make it even more complicated. What we're going to do is we're going to rewrite p of x as this complicated thing here. Okay, so why is this even true? So one way we can think about this is if I have p of z and x, the joint probability, we know we can write that as p of z given x times p of x, right? That's just conditional probability. And then from here, you can see that if you want to isolate p of x, you can write px in this really weird and complicated way, which is the joint pz and x divided by the conditional pz given x. Okay, so why would we ever want to do this? I'll try to explain, but basically that's what's happened here. This has been written as this ratio, and then these guys you can see cancel out. Okay, so hopefully you can now see that this is equal to this. Okay, any questions on that? All right, so now we have this thing. Now this is all inside a log, which means that the log of these products and ratios can be broken up, and then you actually get different integrals. So the first one is just going to be log of this. That gives us the first integral. The second one is going to be log of this guy. Since it's in the denominator, we can move it to the numerator as long as we negate, and so that gives us this guy. And the last one is log of this ratio, which is over here. Now these have different meanings. So if you notice, the first one is very similar to the Q function in EM. The second one is something known as entropy, the entropy of this distribution. And the third one is known as the Kullback-Leibler KL divergence. Now the important thing is that the KL divergence is basically a way of measuring the similarity between two distributions, in this case this one and this one. And the smallest it can get is 0. It can never go negative. And it reaches 0 when these distributions match. You can kind of see that because if you set the numerator and denominator equal, the ratio is 1, and log of 1 is 0, at which point this whole thing goes away. Right? So the key point is that we took our log likelihood and we wrote it in terms of this thing plus something that is 0 or larger. So that means if I remove this, that this thing must be equal or smaller to the log likelihood because I removed something positive. And that means that this is a lower bound on the log likelihood. So here we're writing the lower bound. So these are the first two terms. The likelihood is greater or equal to those first two terms. And this thing we're going to call script L. This is like the lower bound on the log likelihood. Now this lower bound, it depends on our choice of p hat. So as we said before, if p hat is chosen to exactly match this PDF, then this whole term goes to 0, and this bound is exact. There's no gap between this and this. But as our p hat gets farther from this, there's a bigger gap between these two things, the true log likelihood and our lower bound. Okay, so basically, what happens in the EM algorithm is we iterate two steps. We optimize our lower bound, and we maximize over theta. Let me show you an example of this. So imagine that this over here is our log likelihood. This is our log p of x given theta. And I'm writing this as a function of theta. So this thing is very difficult to optimize with gradient ascent, right? Because it's not differentiable here, and because the gradient, basically just the slope, is equal for all the points to the left, and it's equal for all these points to the right. So if you think about what happened if you tried to use gradient ascent to find the peak theta, you would basically, anytime you were to the left of here, you would take a gradient step, which would move you to the right with a fixed amount, according to your step size. And then as soon as you cross this, you would move to the left a fixed amount. And you would bounce back and forth, and never converge. You would never figure out that this is the optimum with a fixed step size. So, and we probably wouldn't even want to try gradient descent because, it's non-differentiable. So what if we try a different approach? And that is kind of inspired by what's happening on this page. Let's say that we come up with a lower bound on our log likelihood, which is perfect at this guess of theta. And then we optimize our lower bound. We find the theta that maximizes this quadratic lower bound. That's easy because it's quadratic. I can find it in closed form. It's going to be right here. And this is my new guess of theta. Now with my new guess of theta, I do this again. I come up with a quadratic lower bound that's perfect at that point, and I optimize that. And that gives me this theta. And then I repeat. I do a new quadratic lower bound, optimum there, or perfect there. I optimize that. It gives me here. I will eventually converge to this peak value. So that's essentially in spirit what EM is trying to do. It comes up with a lower bound on the likelihood that is going to be perfect for one choice of p hat, which was when p hat equals this. And then it will optimize theta for that lower bound. It will optimize the theta of this, and then it will come up with a new lower bound based on the new theta, and so on. Okay, so this is basically where we get this, and that is why, so here's a few details. So this procedure I just described is actually a little bit more generic than EM. It's known as majorization minimization, and EM is just one of the famous algorithms within that class of algorithms. So basically for EM, we take our likelihood based on our guess of the parameters at step t in the algorithm, and we write this as the lower bound plus this KL term. And if we really want to make this lower bound exactly match that, we know that that's easy. Just choose our belief on Z to be this. And this is exactly what is done in KL. This is our belief on Z that we're using here. And then, once we have that belief on Z, we take that Q function, or that lower bound, and we maximize that over theta. So the second one is not a function of theta, so that goes away. That means I just want to maximize this over theta. And that's exactly what this step does. Okay, so this is basically how the EM algorithm works. You use some hidden variables that allow you to create this lower bound, and then your hidden variables and your previous guess of theta gives you a lower bound. Then you optimize theta, you come up with a better lower bound, a better lower bound, and a better lower bound, and so on. Eventually you converge to the solution you want. So one of the reasons we're doing this is so I think that's probably a good explanation. Okay, so that's sort of what EM is doing generally, and how we can motivate it and how we can understand it in the context of maximum likelihood. Is this making sense, or any questions on this? And it's a lot to take in just a few minutes. But these notes are here for you if you ever want to come back to them for in your future life. Maybe you'll need EM. And anyway, I think this is a decent explanation of it. So now that we have EM, we basically want to apply it to our Gaussian mixture model fitting problem. So the key thing is, how do we select our hidden variables? So not surprisingly, we're going to use these kappa i's. Remember, these are discrete. Kappa I tells us which mixture component the ith sample in our data set comes from. And so on the previous page where you saw that Z matrix, really that's just going to be a vector of kappa 1 through kappa n, which we can write as a boldface kappa. So here's our Q function in this case, written with the kappa vector instead of Z. And we can simplify this in a couple ways. So first, this is our joint distribution of all our data points and our kappas. And we always assume that our data points are IID. So we have really a product distribution over the individual xi's and the individual kappa i's. And because we have a log of a product, we can rewrite that as sum of a log. And we can bring the sum outside, at which point we can integrate out all the kappas except for the I, for which the I for whatever index of the sum we're in. That allows us to go from this multidimensional integral to a single dimensional integral over a single kappa I. And finally, you might say, well, kappa I is actually a discrete random variable, so why are we writing it as a PDF? We should really write this as like a PMF or a probability, and we shouldn't be integrating over it, we should be summing over the different possibilities K. So let's do that. So now we're summing over K from 1 to capital K, and we have probability that kappa I equals that value of K. And so that's how we get to this point. And then this last thing, this is the joint probability of xi and kappa I, which we can write as the conditional probability xi given kappa I times probability of kappa I. And so now we've written things in a way that we know all the forms. So this is something we derived a few pages ago. This is probably the most important quantity. So what does this mean? This is the probability that the ith sample comes from the kth cluster or kth mixture components based on our guess of the GMM parameters at iteration t. So essentially at each iteration, we're going to compute these quantities for all samples I and all hypothesized k's. And then this other stuff, this conditional probability is just our Gaussian, and this probability is just our weight. Okay, so these are the ingredients. And finally, okay, yeah, that's the setup. So now EM algorithm has the M step, which is maximizing this. So we basically need to maximize over our parameters, and we have a bunch of different parameters. We have our gamma k's, we have our mu k's, and we have our q k's. So these guys must sum to 1 and be positive. These ones are mean vectors. These are covariance matrices. So this is a big job to do this as a joint maximization. Can't do that. So let's just do it. Let's approximate it as one at a time. So what we're going to do first is let's do the optimization, the maximization over these gamma k's. So we're going to have to force the fact that they must sum to 1. We don't have to force the positivity that will come naturally, but we do have to incorporate this. And we learned, I think back in end of Unit 6, we learned that if you have an equality constraint like this, you can use the Lagrangian method, which takes the original cost function, which is just this part, and then adds on lambda times that constraint rewritten to be 0. So now lambda is a new optimization variable that we have to optimize in addition to all our gamma k's. So this is our new objective. And now we just take our standard approach of computing the gradient, setting it to 0. So we compute the gradient of this with respect to gamma k and set that to 0. And when we compute the gradient, this turns into a 1 over gamma k. These guys just turn into 1. And so you get this nice expression here. And if this is true, if this equals 0, then we can multiply both sides of the equation by gamma k, and then that must be true also. And if this is true for each k, then you can sum this over k on both sides of the equation, and that must also be equal to 0. And finally, we can leverage the fact that we know these must sum to 1, and we know these must sum to 1 for each I, and that simplifies things dramatically. And this is a sum of the value 1 from I equals 1 to n, which is n. And at the end of all this, we have figured out that lambda must equal n. So we're halfway there. Now that we know lambda, we can figure out what are all the gamma k's. So to do that, we come back to this equation. We can rewrite this as gamma k must be equal to 1 over lambda sum over I gamma k I t, but we know that this thing is now n. Okay, so basically this is what we have. And finally, this is the optimum value for gamma k. So from the previous step, we computed these guys for every k in I, and now we just average them over I to get the next version. So this is the next gamma k. Okay, so we did the optimization over gamma k. Now we can repeat this for mu k. It's a little bit easier. So we want to set the gradient of this term with respect to mu k to 0. Because we have log of a single Gaussian here, that's nice, that's just a quadratic. We can do, in this case, vector calculus and find that this gradient is just going to be this, and rearrange it a little bit by pulling the Q matrix out to the front. And finally, we know that the 0 vector must be Q matrix times this vector. And since the Q matrix is invertible, it's full rank, the only way to make this side 0 is actually to make this quantity 0. And making this quantity, if that quantity is 0, we can solve for mu k, and that gives us the update for mu k. Okay, and I'm not going to go into the details, but a very similar approach can be used to optimize qk. And here's the final algorithm. So you initialize, at iteration 0, you initialize all your GMM parameters somehow. Then you just iterate these steps over and over. For all samples I, for all cluster components k, you compute these probabilities according to this equation. Then you average those probabilities over I to get your new gamma weights. You do basically something that looks like a sample mean over the xi's, except you have these weights in there. That gives you your mu k, and something again that looks like a sample covariance, but with these weights, and that gives you qk. And now with these updated things, you plug them back into here in the next step, and you go around and around. So for initialization, it's common to use k-means plus. You run that algorithm, and then you use its values. So whatever fraction of samples k-means plus assigned to k, you set that at the gamma k, and you can compute the mean and covariance of those samples to get your initializations here. And if you want to save complexity, rather than estimating a full covariance matrix Q, you just approximate it as diagonal. So let me show you a pictorial example. Again, from the Bishop book, like our k-means example was. It's a really nice book for probabilistic viewpoint on machine learning. So here's our data set. And this is how we're initializing the two means. So one of them has the mixture components. This has a mean here, and it has a scaled identity covariance matrix, which means instead of an ellipse, you just have a circle that tells you basically, like this is sort of representing like the standard deviation of your initial guess of the blue component. And then you have a red component, which has a mean here. So the first step is for each of your data points, you compute the probability that this point came from this cluster. And you also compute the probability that it came from this, which is just 1 minus. And so now that's being shown using shading. So if the probability is 1 that it came from this, that would be purely red. If the probability came from blue one is 1, that would be purely blue. And if the probability is like 0.5, then that would be a purple point. So here the shading of this picture shows you, or the color shows you the probability that it came from this versus somewhere in between. And now that all these points are colored, meaning we know the weights, we basically just use that as a weighted average to get the conditional mean, which is here. And then the conditional covariance is like, weighted, again, covariance, which gives you this. And you do the same for the blue weights, and you get this. So you basically started from here, and now you have an updated Gaussian mixture model. And then you just repeat. Using these new Gaussian guesses, you compute all the colors for the points, all those gamma k weights. And then you again do your sample mean and everything. And basically, this is second iteration, then fifth iteration, then 20th iteration. You can see that gradually the Gaussian components start to fit to the data. And so now you're saying there's a cluster with a mean here and a covariance matrix that characterizes this, and we have another cluster here, that mean and that covariance matrix. And I don't know what the weights are. There's a lambda 1 and a lambda 2. Probably this is going to have a larger weight because there's more points closer to that than this one. Okay, so that's kind of a visualization of the EM algorithm in action. Hopefully it's making a little bit more sense in the context of clustering. Any questions on this? Okay. Let's just do a quick comparison between EM, GMM, and k-means. They're actually very similar, but yet a little different. So EM is computing these soft assignments. These are numbers. Whereas k-means only computes hard assignments, like which cluster did it come from. EM estimates these covariance matrices. K-means doesn't, but if you think about it, it's kind of like it implicitly estimates scaled identity covariance matrices with super tiny epsilons. And as a result, k-means gives us those piecewise linear boundaries, those Voronoi cells, whereas EM actually gives us curved boundaries. So we could have some curved boundaries depending on how things look. And then EM estimates weights for the Gaussian mixture components, whereas k-means doesn't. It basically implicitly assumes all the weights are equal. EM is going to be a bit more computationally expensive than k-means, especially if you estimate the full covariance matrix. Both methods can get stuck in local minima. Both benefit from good initializations. Both are implemented in sklearn, and it's pretty easy because they did all the stuff for you. You just run Gaussian mixture, and it basically runs this algorithm that we derived here. So that's basically the algorithm. Any questions? So the very last thing is just to show you sort of a nice demonstration of this. The problem the application is going to be color quantization. So it goes like this. So most images that you work with, color images, as we know, have red, green, and blue channels. And every pixel, basically you get 3 numbers, which is the brightness of each, right? And each of those brightnesses are typically 8 bits, 1 byte. So it means like for the red channel, there's a total of 256 different brightnesses. And when you look at the values of the image, they're integers from 0 to 255. I think we've seen that before. So the red has 1 byte, the green has 1 byte, the blue has 1 byte. The total number of bits for all 3 together is 24 bits. And if you think about how many colors can you describe with 24 bits, it's a lot. It's 2 to the power 24, which is almost 17 million colors. So even though it might seem like, 1 byte is not really that much per channel, it adds up to a very sophisticated color palette. 17 million possible colors. Okay, but as we know, that means that every pixel in your image takes 3 bytes to represent. So this is like basically some sort of compression idea. What if, instead of allowing my image to use all these 17 million possible colors, what if I only allowed it to use 16 colors, but I got to choose those 16 colors? I want to find the 16 colors that are best fit to my image, and then I'm going to sort of quantize my image to those 16 colors and represent it that way. So now, instead of 24 bits per pixel, I'm only using 4 bits per pixel. So, compression by a factor of 6. So this is actually a clustering problem. Let's think about it graphically. So we have like a red, green, and blue color space. And what I can think of now is every pixel in my image is a dot somewhere in this red, green, blue color space, right? And if I, plot all my dots, I have a whole bunch of data points. And maybe there's some regions within here that are more dense than others. And those dense regions are where I want to put my new colors. So maybe I put like 1 new color over here, 1 new color over here, 1 new color here and here. And in this case, I would have 4 colors total. So the question now is, where do I put those 4 points? And you can see it's basically a clustering problem. I want to put those points, those 4 cluster centers, those centroids, close to where I have a lot of data points. So in this case, we have three-dimensional features. Those are the red points there. We're going to have k equals 16 centroids. And we could do this with all 273,000 pixels, but that's computationally a lot. So what we did in this demo is we just looked at 1,000 random pixels in this image. And based on those 1,000 random pixels, in other words, 1,000 red dots here, we did the clustering. And we used both. We tried k-means and we tried EM, and then we can compare the performances. So is the overall approach kind of clear what we're doing? Okay, so let's kind of take a look at the original ground truth image. You can see there's a range of different colors, and what's going to be especially difficult to do is capture the very fine variation in color as it gradually goes from blue to pink to white. And when you look at this horizon, you can see there's like a very gradual change. Somehow it's going to have to choose 16 colors, to cover everything here. And I also want to point out that there's an island here with a bridge connecting to the mainland, and those are the details that we might lose once we quantize. So first, let's look at what happens with k-means. So basically here you can see it chose, one sky color here, another color here, another color here. But basically for the sky, it's only allocated 3 colors. So you get these, basically sudden transitions in color. And you can also see that it's basically the island and the trees here, they get 1 color, and now you can't even really tell that it's an island anymore. So this is what happens with k-means. And now, based on what we know between k-means and GMM is a more sophisticated model. It instead of sort of fitting Voronoi cells here, it can fit these ellipses. It can kind of customize itself to the shapes that you might have in your data, the densities. And so let's look at how it does. You can see for the 16 colors, it does a much better job. You can see the island. The sky is, of course, only 3 colors, but that's what you're going to get with 16 colors total. But you can see it did a much better job of getting different layers here and so on. So just a nice comparison between EM-GMM and K-means. EM-GMM works a little bit better, but it's a little bit more complex to run. So that's it for this unit. Any questions on anything? Okay, so again, lots of math here. Apologize for all that, but I don't expect that you guys are able to take it in real time. I certainly wouldn't be able to do that, but it's a reference. It's maybe you learned some high-level stuff, and if you ever need to come back to it, you have these notes, and you can dig into them then. So this covers Unit 12. Actually, there's a couple more. Let me just talk about one thing briefly. Is that both of these methods require that we tell them the number of components, and in practice, maybe I don't know that when I'm clustering. So there's other methods that actually can try to learn the number of components, and there's a nice scikit learn tutorial sort of thing on clustering, and it shows these different methods. So here we have a version of K-means, mini-batch K-means. We have Gaussian mixture, which is the EM stuff, and we have all these other ones. And it's sort of interesting to look at how these different methods work. There's, for some of these problems like this, like K-means just has a really hard time, but Gaussian mixture model does it perfectly. But then there's other ones that if you think about K-means here, it's just going to have to basically come up with some linear partition. There's no way it's going to be able to handle this. Same thing with Gaussian mixture. But there's other methods that are more sophisticated that can come up with, you could say decision boundaries that are nonlinear. And so we didn't talk about those, but they're out there. Some of these methods, I think they all do well with this. And some of them have a hard time, even though they're sophisticated, they have a hard time like getting the big and the small clusters, although Gaussian mixture does great. K-means does something a little weird. It's sort of insightful. And it's also interesting when you give it something like this, basically one big cluster, what does it do? K-means splits it into 3, but some of these other methods kind of just keep it together. Anyway, just shows you a few other methods out there. So that's finally it for this unit. And then the last unit, which I can start presenting next week, I just finished making a unit on transformers and large language models. So it'll be the first time I'm teaching that material, but I'm excited to do so. And on Monday, I'll start that. And then that will just be 1 or 2 lectures, and then we'll be done. All right, so have a great weekend, and I'll see you guys then.